So in this example, we have four charges arranged in a square configuration, and we want to find the electric potential for a fifth charge that's placed at the very center. All right, so let's see. The values for each of these charges, the magnitudes, right? Well, the value is 1 nanocoulomb, right? 1 times 10 to the minus 9. And the squares of side length 0.2 meters. All right. And so if we have a fifth charge placed at the very center, we'll call it capital Q. And capital Q has a value of negative 5 nanocoulombs. What's the electric potential, right, for that charge? That's what we're trying to determine here. So this is a discrete charge configuration, right? There's only four charges. So it's a little easier, right? It's a different type of solution than for a continuous distribution. But let's take a look. So it would behoove us to find the distance from capital Q to each of these other charges. Right, that happens to be the same distance. I'll call that lowercase r. And so if we make this right triangle, each of these side lengths are a over 2. We can go ahead and find the distance, because we'll need it later. Let's see. All right, and so a little math. This is 2a squared over 4 square root, which is a over root 2. All right. So for discrete charges, the potential can be written like this. We have V equals the Coulomb constant times the sum of I equals 1 to however many charges there are contributing to the overall potential. In this case, there are 4, right? 1, 2, 3, 4. So I equals 1 to 4 of keeping the same format for the electric potential of KQ over R. Thus, we have Q sub I over R sub I. Okay? Yes, I know the distances are all equal, but just bear with me. And so what we do is, well, superposition tells us that we can calculate the potential at the center here based only off one charge at a time, right? So Q contributes to the potential, its amount, and that's completely separate from the amounts of the other charges, right? So we can just take them each in their own terms and add them up. So we have K times Q1, which is just Q, divided by the distance between Q and the center, which is R. And that's it, right? That's our first term at least. The second term, K times Q2, which is a magnitude of 2Q over R. For charge 3, K over 3Q over R. And the fourth term, 4Q. Okay? And that's basically it, right? We add up and see what we get. So factoring out all of the commons gives us KQ over R, and then 1 plus 2 plus 3 plus 4. Okay? So K has a value of, well, actually, what's that? 1 was 3, was 3, 6, 10. So that's 10. I like prefactors in the front. Times 9 times 10 to the 9. Now, the charge here, we're using lowercase q, not capital Q in this case, right? Capital Q is, if you remember from voltage, right, delta V is the same, or is defined as delta U divided by the charge. So in this case, it's the change in potential energy per capital Q. Because capital Q has, what is that, 5 times a larger charge than the individuals at the corners, it'll have, well, kind of a a lower potential than if, say, Q were at the center, right? So in essence, we use this 1 nanocoulomb. The charge in question is not used in the actual potential calculation, right? And then the value for R was our A over root 2, which is 0.2 flip and multiply root 2. Okay, so if we plug in all of these numbers, notice it's positive, we get 636.4, at least is what I got. 636.4 volts, right? Which is a considerable voltage, right? That 5 nanocoulomb charge will zip away, right? So remember, if the voltage is positive, then the charge will be pushed to, right? That's the change in potential energy. So let me write that here. Per Q. So this means that the change is positive. And because Q is actually a negative, it will be attracted to these charges. It'll be attracted, somewhere, right? So it'll increase potential energy, right? But that's effectively how you solve for the electric potential for a set of discrete charges.